So we're gonna start this video with 4 definitions, and I'm not a big definition fan myself, but we are gonna need them. But let's make it a little bit more interesting by kind of thinking about where they're going. This first one, f is continuous from the right. What do you expect from a definition like this? Remember, a function's continuous if the limit exists, the function exists, and they're the same. So what does continuous from the right maybe imply? Well, maybe instead of looking at the two-sided limit, we look at the one-sided limit. And it turns out that's exactly what it is, okay? So it's continuous from the right if the limit value from the right of that function equals the function value right there. And again, technically right, continuous from the right at A. And so this next definition is really just a lot of the same. Continuous from the left, you know what's going to go here, right? If the limit as x approaches A from the left of the function equals the function value. Continuity at a point, limit equals function. Continuity from the right at a point, limit from the right equals the function, and same for the left. Now we get to the two definitions that are really something that we care about. So this next one, f is continuous on an open interval a to b if, so continuous at a point, we have that definition. Continuous on an interval should just be continuous at a lot of points, right? If it's continuous at every point in that interval. And we have one last definition of continuity, and this one might kind of surprise you a little bit. And the reason why it comes from, so you don't have to necessarily write this down, or if you do, write it down somewhere else. I don't have room without changing my page. Let's look at the square root function. We might want to know, is this function continuous everywhere on its domain? Now my gut says, yes, this is continuous everywhere on its domain. It's connected everywhere, right? You don't have to pick up your pen or your pencil to draw the square root function. I think it's continuous. But it's not continuous at 0, 0. So it's not continuous at every point in its domain exactly. Why is it not continuous at this point? Because the two-sided limit doesn't exist. It's continuous at a point if the two-sided limit equals the function value. The one-sided limit equals the function value, but there is no limit from the left because the function is not defined from the left, right? So we have a slightly different and honestly more useful definition for continuity on closed intervals. So f is continuous on a closed interval or on a partially closed interval. There's actually like 3 definitions that you can put here. They're all basically the same. If it's continuous on the open interval and it's continuous from the right at A. So a function's continuous on a closed interval if it's continuous on the inside, and then at the ends, we only care about the one-sided limit at the end. So in this case, that square root function would be continuous on that closed interval, even though technically our regular definition of two-sided continuity doesn't exist at the end. All right. So those are the definitions. And again, you could change which part is closed, and then we'd say continuous from the left at B, or we could have them both be closed, and then it would have to be have one-sided continuity at both endpoint. All right. And the way to remember that it needs to be from the right at A here is because that's the part of the interval, right? To the right of A, that's the things that we're actually talking about. We're looking from A to B. So right of A, left of B. Those are the things that we can work with. These are our definitions that we're going to use here on the next page. Example 4. On what intervals is, that's quite the S, is F continuous? Oh no, the student has gone to sleep. Hopefully you are staying awake better than my cat. It's because last night she climbed up my green screen 3 times. I have a spray bottle. I was really active last night. Didn't get too much sleep. So this function is equal to x minus 1 divided by x squared minus 2x plus 2x. Not that it really matters. So immediately, we're at this point in the section. You should think, boom, rational function, rational function, rational function. What did Jason say about rational functions? Jason said rational functions are continuous everywhere on their domains. Ah, okay. We actually kind of already talked about this, right? Rational functions, continuous on their domains. And did we literally do this exact problem? I'm getting some weird deja vu. But I mean, I have taught this class before, but I don't know if I've done this problem today. Rational functions are continuous on their domain, and the domain, right, is everything except when the denominator is equal to 0. So we have to say, okay, when is the denominator equal to 0, right? If we can find out when the denominator equals 0, then we know the domain. To solve this equation, we factor. Take out a common factor of x, and what's left over is x plus 2. So the denominator is going to be 0 when x is equal to 0 and when x is equal to negative 2. So the domain is just everything except for that. The set of all real numbers x such that x is not equal to 0 or negative 2. That's where it's continuous. So it's continuous. And again, you can use set builder notation again, or you could use interval notation. Set builder and interval notation are both great. I'm probably never going to require one or the other, but if I do, I'll tell you. So continuous on the interval from negative infinity up to negative 2, and then negative 2 up to 0, and then 0 up to positive infinity. Which means it's continuous at every single point in that interval. Every single point here, and that's a lot of points, infinitely many of them, uncountably infinite, because there are different concepts of infinity. There are different sizes of infinity, which is kind of fun to think about. That's not for this class. There are infinitely many points where this is continuous. There are infinitely many points of this function, of this rational function, where the function exists, and the limit exists, and the limit and the function value at that point are the same. But there are 2 points that have infinite discontinuities, because those are those vertical asymptotes at x equals 0 and x equals negative 2. Tying everything together, hopefully. Let's do another part, and then we'll do some theorems and some extra fun, optional fun. There's optional fun at the end of this video. This video is going to be much longer than it needs to be, but you can always just quit early. I'll tell you when the optional part happens. Optional fun. Where is this function continuous? Where is this function continuous? Fun fact. No, I'm not going to tell you the fun fact. No, we'll save the fun fact for later. But if you know what this function looks like, power to you. All right. So we can use limit laws to evaluate limits here. Okay? Everywhere the limit exists, limit laws are going to work. Okay? So limit laws, give us that the limit as x goes to some point of this function, right? We can take the limit inside the square root, and then it's a polynomial, and we can evaluate at that polynomial. It's going to be square root of 4 minus a squared. With that root law, and with the theorem about polynomials being continuous. So the limit is going to exist whenever this exists. Right? So the limit exists when this exists. So when is this a real number? Well, it's a real number when the inside's positive. So it's going to be real when 4 minus a squared is positive. Now be very, very, very careful. In most math classes, we talk about finding information, solving inequalities for linear inequalities. Solving nonlinear inequalities is very different. So just be very, very careful if you're solving an inequality like this. All right. Usually graphically is a great way to do this. You can plot this function 4 minus a squared, see when it's positive, or you can do it algebraically too, but just be very careful. Let's look at 4 minus x squared or 4 minus a squared. Yeah. So when is this function positive or 0? Between -2 and 2. So it's real when that is greater than or equal to 0. That's the interval from -2 to 2. All right. And if we're actually really, really particular, the two-sided limit only exists on the open interval. Why does the two-sided limit only exist on the open interval? Because this function exists on the closed interval, but not outside of that. Right? The function exists at the edges, but the two-sided limit doesn't exist at the edge. Because this function does not exist. We know this. Continuous on that interval from the limit laws. So to see whether it's continuous on the closed interval, we have to utilize this part of the definition. It's continuous on the closed interval if it's continuous on the open interval, which we have, and it's continuous from the right of the left endpoint and from the left of the right endpoint. Kind of feels weird to say. Where is this? What is this? How did this get here? This is where we're supposed to be. All right. Check if it's continuous on the closed interval. We know it's continuous on the open interval from limit laws. So to see whether it's continuous on the closed interval, we have to look at the limit as x approaches the left endpoint from the right. And again, you always remember it because if we're approaching this one, we have to approach this from the interval. So to the right is when we're still in that interval of this function. And again, limit laws give you this as well. This actually, again, by limit laws, is going to give you that this limit equals 0. And again, f of -2 is also equal to 0. This first one from limit laws, I'm not going to do it all out. And you can do the same thing for the other one-sided limit. So similarly, the limit as x approaches +2 from the left of the function equals 0. And again, the function value at 2 also equals 0. So by all of these things, so this tells us it's continuous in the open interval. This says it's continuous on the left endpoint. Well, it tells us the left endpoint can be closed. We have one-sided continuity at the left endpoint. And this third thing tells us that we have one-sided continuity on the right endpoint. So we can conclude that f is continuous on actually that closed interval, -2 to 2. Let's visually look at this last one. Okay. If we're looking at the function y equals the square root of 4 minus x squared, this is a semicircle. So again, two-sided continuity makes no sense here at this point because it's not defined to the left. But we know it's continuous on the open interval. We proved that with limit laws. And it is continuous here from the right. It is continuous here from the left. So that is the definition for what it means to be continuous on a closed interval. All right, and that's probably the weirdest thing in this section, continuity on a closed interval. So ask me if something's unclear about that or if you have any questions about it. We're going to finish with 2 quick theorems and then a little bit of bonus fun. All right, the theorems are important though. Composite function theorem. Is a theorem about composite functions. Functions inside of functions. So if f is continuous at L and the limit as x approaches a of that function equals L, then the limit as x approaches a of the function composition is equal to something. And this is like the very tiniest hint of this really profound area of mathematical study, which is when can limits pass through things? In some areas of mathematics, this limit is on the outside and we can bring it into the inside. And that's what's happening here. And there's some really, really complicated, complex, full fleshed out theory for super abstract versions of this. This is kind of the first little taste. So as long as f is continuous, we can bring the limit inside. And specifically, as long as it's continuous at this point. What point is this? Well, this inner limit is L. So as long as f is continuous at that point, we can bring that limit inside. And again, we could simplify this a little bit. That inner limit is equal to L. That's a composite function theorem. We'll use it a little bit, but it's not going to be used a ton. But it's a very, very profound. Sound like my math teachers. It's very big. It's a very big thing, actually. Being able to move limits around like this. All right, last theorem. And then this video will mostly be done. Basically be done. All trig functions are continuous on their domains. All right, know this, use it. That's basically it for this video. You got 2 options going forward. You can be done with this video. You can pause, close out the video right now. Or you can pause the video, take a little break, and then come back for some bonus fun. I'm going to prove most of this, pretty much all the important parts, for the 6 trig functions: sine, cosine, tangent, cotangent, cosecant, secant. And it's actually not as bad as you might think, but also kind of worse than you might think too. All right. You don't need to know this proof. You don't even need to understand this proof, but I think it's instructive and I think it is good little practice tying things together. So I am including it in this video, but it is optional. Again, you could have already closed the video. You don't even need to be watching this unless you're interested, because I think it's fun. I want to do it, which is why I'm doing it. I'm not forcing you to do it. So we want to prove that all trig functions are continuous. If we can do it for sine and cosine, then we can basically do it for everything. Because tangent is just sine over cosine. So limit laws would give us tangent. Same with cotangent. It's just cosine over sine. And, well, secant is just 1 over cosine. Cosecant is just 1 over sine. So if we can do sine and cosine, we can do everything. And the proof for sine and cosine are basically going to be identical to each other, almost identical to each other. We've got some tricks for doing this. All right, so we're going to want, we want to show that sine, am I doing sine? No, let's start with cosine. We're going to do cosine. I did have this in my notes just to make sure that I didn't get stuck on the video because I haven't actually proved this before myself. We want to show that cosine of x is continuous everywhere, at all points, at all real values of a. So to show something is continuous, right, what do we want to do? We want to say that cosine of a, the function value, equals the limit. So we're going to look at the limit and prove it for everything. And we're going to do a lot of little tricks here. So before we even do this, before we even start, remember, and you may or may not have seen this identity before, but the cosine, this is called the sum identity for cosine, is the cosine of the first angle. So if we add two angles together, the cosine of that is the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle, I think. Let me just double check. Yep. All right, that is our identity. And that's the big thing that we're using here. So let's start. If we want to prove equality, remember back from earlier classes, if we want to prove two things are equal to each other, we start with one side and hope that we can get to the other side. So let's start with the right, do some tricks. A lot of math proofs just involve little tricks. And then we're going to use the composite function theorem to prove this. All right. So the limit of this function, I'm going to write something down and I want you to think about whether it's true. All right. This is going to be the limit of the cosine of x minus a plus a. Now you might be going, Jason, please don't, stop being ridiculous, Jason. Of course this is true. Subtracting a, adding a, this insight just simplifies to x. This just simplifies the cosine of x. You're just unsimplifying, Jason. You're just making things worse. Am I? Well, now I have two angles, right? This is an angle, and that's an angle. I said we're going to use this addition formula for cosine, the angle sum formula for cosine, so let's use it. The cosine of one thing plus another thing, the first thing is x minus a, the second thing is a. We're still true. We can subtract and add a. It doesn't change anything. Now we can use angle sum formula. So this is, the limit is still on the outside. The limit is just relaxing a little bit. Now let's use this blue formula up here. Blue formula says cosine of the first times cosine of the second. So cosine of the first thing times the cosine of the second thing. Right? First thing, second thing. Minus the sine of the first thing times the sine of the second thing. Still true. That's an identity. True for all values of x and all values of a. It doesn't look any better. It doesn't look like we're going to get here. But have a little faith. All right, so now we can use some limit laws. All right, we have two things added, we have things multiplied, and as long as all these limits exist, we can use limit laws to simplify a little bit. So this is going to be the limit as x approaches a of the cosine of x minus a times the limit as x approaches a of the cosine of a. Right? As long as these limits exist, and we'll show that they do, this is valid. Minus the limit as x approaches a of the sine of x minus a times the limit as x approaches a of the sine of a. So we have 4 limits. We started with 1 limit, and now Jason's giving us 4. 2 of these limits are really easy, and 2 of these limits are very similar. So look at this limit right here. This is the easiest limit of your life. This is the limit of a constant. This doesn't have anything to do with x. The limit of a constant function. Cosine of a is always the same thing, no matter what x is. I don't care what x is, the cosine of a is equal to the cosine of a. Right? And same with this one over here. I don't care what x is, the sine of a is just the sine of a. So I'm writing the sine of a beneath my big head. So the only ones that are a little trickier are these other 2. And we need to use the composite function theorem. Composite function theorem says if we have function composition, and we do have function composition here, right? This is the cosine of this linear function. It's the cosine of, so cosine is our outside function. X minus a, that linear function, is our inside function. We do have function composition. All right. Then the limit can go inside as long as the function's continuous at that point. So the limit can go inside as long as cosine's continuous at that point. Now, you might be thinking, because I've literally been in your shoes not that long ago, you might be thinking, we can't use a composite function theorem. We're trying to prove that cosine's continuous. But in order to use a composite function theorem, it has to be continuous. So we can't use something that we're trying to prove. But here's the distinction. Composite function theorem says it only has to be continuous at a single point. We're trying to prove that cosine is continuous everywhere. So it's hard to prove something infinitely many places, but we can prove it in just one place, no problem. So if we can prove that cosine and sine are continuous at 0, right? 0 is the limit of this inside function. As x approaches a, this inside approaches 0. All we have to do is show that cosine and sine are continuous at 0, and we can use the composite function theorem and get something really nice. Okay? So, this is what we need. Our cosine of x and sine of x continuous at x equals 0. And again, to prove this, we have to use the definite formal definition of a limit, which we're not going to talk about in this one. But yes, you can prove this. But to formally show that the limit equals the function value, you do have to use 2.5, which we're skipping in this class. But it's not that bad. It's not bad at all, honestly. So we can have this. We can use a composite function theorem to say that this limit can go inside. So if we do that, that gives us that the cosine of the limit as x approaches a of x minus a times the cosine of a minus the sine of the limit as x approaches a of x minus a times the sine of a, making sure I'm copying it down correctly. Right? Composite function theorem lets us move that limit inside. And now this limit is super easy to evaluate. This is the limit of a linear function. It's a limit of a polynomial. We can just plug in a. We just plug in a, right? What is a minus a? 0. And again, what is a minus a? Still 0. Now things are finally starting to look a little nicer. Cosine of 0 equals 1. Sine of 0 is even better. It's 0. What are we left with? Just cosine of A. We wanted to prove that it's continuous at all points. So we picked an arbitrary point and showed it was indeed continuous there. And there are other methods of proving this as well, using the definition of the limit. But this is one way to kind of combine everything and show cosine of x continuous for all real numbers A. You do the same thing for sine, and then use limit laws to show it for tangent, which is just sine over cosine. Really quick to do tangent. Really quick to do cotangent, secant, and cosecant as well. We've basically proven it for all of them, and it took a while. But there's some cool logic in here, kind of utilizing a bunch of concepts. All right, that's basically it. Add a little extra math here. We have one more video on the intermediate value theorem, which is kind of cool. And then the homework questions. So there's a bunch of cool homework questions here. All right, this video is long enough. Bye-bye. Goodbye. Go away.